and see if you could find an example of multiple regression being used. And let's take, I don't know, 15 minutes or so and talk about how it has been used and in the literature. It'll give us an opportunity to see how authors have used it and what language they use to describe it. Let's see if they talked about assumptions or anything like that. Right? So I'm going to assume you all did it, so I'm not going to ask who did the homework. So who'd like to read something that they found interesting? Nobody found anything interesting?
Well, I'm like a little scared to go.
Well, that's why we're here, Lisa, because let me say this, right? Let me give you an observation, right? I teach here and I teach at PCOM, right? And I'm going to tell you that the difference between the classes between here and PCOM are nearly night and day, right? The students at he's laughing.
Are they medical students?
Yeah.
Are they like?
They're osteopaths, yeah.
Yeah,
Right,
they're
like
like
other schools.
Yeah.
but they're not like in the master's.
No, they're osteopaths.
They're geostudents,
Yeah, they are geostudents.
Makes me feel.
They're not afraid to ask questions. Yeah, whereas here, not only here in this class, but in like the School of Education and other places that I teach at Penn, I think the students here are afraid to look dumb.
Yeah.
And the feedback that I constantly give students here at Penn is, look, if you knew all this stuff, you wouldn't need to be here, right? Right?
Yeah.
So if you're scared, the other reason I incorporate participation in the class is that it's a safe environment to overcome some of that fear and practice that public speaking kind of a thing too, right? So that's why, we're all in this together. So Lisa, I appreciate you being nervous.
Okay.
And I'm sure other people are too, because as soon as I said that, everyone's eyes became the size of saucers. And that's okay, we're here together to learn together.
All right,
Okay,
well,
so-
let's do it. So I'm just going to tell you like a little about the article.
Sure,
And then
yeah.
hopefully, because there's some parts that I don't understand.
That's fine.
So I used an article because I'm studying, hoping to look at the effective duty hour reform regulations that were implemented in 2011. And there was a study done in 2007 published in JAMA by Kevin Boltier. He did two actually, one looking at a Medicare database and one looking at a VA database. And the basic question is, what was the impact of duty hour reform on mortality? In the 2003 reforms. So they basically use a difference. Am I clear so far?
Sure.
Okay. A difference in difference.
We're talking
Everybody
to
with
that.
the interrupted time series approach, comparing 3 years pre-reform, looking at hospital trends and mortality, to 3 years post-reform. And each hospital then basically is compared to itself before and after for the difference. And then teaching hospitals are compared to non-teaching hospitals. They made, to sort of evaluate the intensity of teaching, they used resident to bed ratio as a continuous variable. And so their primary outcome was mortality, and their big coefficient. So this is where I start to get sort of confused about all this logistics.
So let me ask you this.
Yeah.
When you talked about mortality, did they talk about just whether the probability or the likelihood of a death, or did they count number of deaths? Or when
I
they
think
said mortality, what did they talk about?
Well, I think they looked at number of deaths.
Okay.
And then they developed a coefficient of the resident to bed ratio, and they interacted that with their dummy variable, which is
Before or after?
exactly to present an odds ratio of death.
Okay.
Does that make sense?
Yep.
So in their model, they controlled for patient level characteristics. So they used that Elixhauser that seems to be commonly used in the literature, which uses like 27 patient comorbidities. And then they controlled for hospital level characteristics. So those were the primary adjustments. They don't like present their equation.
Yeah, okay.
And basically, and then they use a fixed effects model for hospital indicators. That's where I started to get a little bit.
Okay, we can talk about that.
Yeah. So does that make sense so far? I don't know what else to say.
Okay, all right. Everybody understand the setup so far? No? Okay, so what Lisa's described is what we refer to as a mixed model.
Oh.
Okay, and you actually looked at binary data, so you looked at a logistic regression, it sounds like, as opposed to multiple regression.
Oh, I see.
Which is okay, because that's why we do this exercise.
I could do another one.
No, that's fine. That's fine.
Such a good example.
So we have this idea of a mixed model where we consider factors or predictors to be either fixed or random. So you might see that a lot in the literature where you say, oh, we have fixed effects or random effects. When you have fixed effects and random effects together in the same model, we call that a mixed model. So let's talk about the difference between the fixed effects and random effects. So when we consider a factor to be a fixed effect, the assumption that we're making is that the observations in our data essentially saturate the variability in the population. So, by that, if I'm interested in studying the effect of sex, or genic sex as in biology, on some outcome, and I have both males and females in my sample, I could consider sex to be a fixed effect because I have, those are the levels of the thing that I'm interested in, right? There's like male, female, and maybe we might have a hermaphrodite, right? But for all intents and purposes, when we think of the variable sex, we think male, female, right? So I would consider that to be a fixed effect. I have sampled my sample, I'm studying all of the levels of the thing that I'm interested in. Whereas a random effect is, my sample, or the observations in my sample, represent a subset of all the possible things that I'm studying. So in the case of what Lisa was describing, I suspect they treated hospital as a random effect. Because probably in the study they didn't have data on all hospitals. They had data on a subset of hospitals. So because they didn't have data on all hospitals, they treated the hospitals that they did observe as more or less random. So with random effects, we actually don't, or we cannot, estimate the coefficient for a random effect because it's random, right?
Good lessons.
We can't estimate the effect of a random effect because it's random, right? What we want to do, you got that look on your face again. You're my barometer.
I don't get it.
Okay, so because it's random, we can't estimate how big or small something is.
How big or small?
The effect is.
The effect of
Of the
variability
random
between-
thing.
Yeah, okay.
Of the random thing that we're studying, because it's random, right?
So is that the whole reason you control for it and just take it out?
Well, not necessarily control for, because you can actually get very interesting numbers from it. So let me keep talking about this a little bit. So the idea of a random effect is, since you can't estimate the effect, like for example in the effect of, if we were to look at a fixed effect for sex, we might look at the probability of being a male increases your likelihood of mortality by 75%. We can estimate that effect, right? With the random effect, we can't come up with that it increases or decreases the likelihood of something, in this case of an odds ratio. What we do with the random effect is we can see how much variance there is in this thing. And that's essentially what we can do. This idea of estimating the magnitude of the variance of this random effects becomes very important. Because in the case of an individual level thing, we can compute what are called interclass correlations, ICCs, which I think you've heard of before. So if I were to measure a set of subjects repeatedly, like so this is a repeated measures kind of design, and I might want to look at the effect of something, of some effects on mortality, and I were to treat my sample as a random effect, what I would be able to do is I would be able to say, well, how much of that variability on that outcome is due to intra-individual variability? And if this has to do with intra-individual variability, we're talking about idiopathic things, right? Things that are specific to me. That's what I mean by intra-individual. So if I'm going to measure things over time within people, I'm going to have variability from my measurement to time 1 to time 2, time 3. So that's intra-individual variability. Those are effects that I can't generalize to other people because that's my own individual variability. Does that make sense?
I just understood. Did you say idiopathic or did you idiosyncratic? Okay.
It would be idiopathic, idiosyncratic in the sense that it's specific to me and I can't generalize these results, my results, to other people.
Okay.
Does that make sense?
All right.
Okay. Now, you follow me?
It makes sense enough for me to try to
Okay.
get your next point.
For things that are not random, I can then say, well, how much of that variability in the total outcome is due to idiopathic, idiosyncratic variability, which theoretically I can't come up with a treatment for because it's my own individualness, relative to things that are external to the individual but are common to the disease. Those are the things that we can treat or develop treatments for. Does that make sense? No?
I think on the sort of outline of how we got from random effects to this, I got lost somewhere.
Yeah.
Okay.
Because what are we talking about? Hospital like being random?
It's the same kind of thing. So if I'm talking about hospital effects, there's going to be certain, you have patients nested within hospitals, right?
Yes.
So they're going to be,
Yeah, nested means a lot.
okay, all right.
Yeah, nested means
So, okay, all right. So let's think about your practice and where you work. Do some of you see the same patient on more than one occasion?
Yes.
Lots of you do. So let's start off by, we're going to build a topology here. Okay? So we'll have the concept of patient, right? Within patient, we have visits nested within patient.
Just real quick, this has nothing to do with fixed or random
It
effects.
absolutely has everything to do
Okay.
with fixed and
Is
random
it-
effects.
Is it exclusive to one of them?
No, we're going to build the topology
Okay.
and talk about fixed versus
Perfect,
random
okay.
and things
Just going to
like
help us
that.
understand the difference.
Yeah, it gets complicated.
Start here.
It does get complicated, but it's all based on correlation.
Well, let's just start with like, I get this.
You got this.
The same patient I see on 4 different times. I'm with
Okay.
you for that.
I'm here.
Yeah.
Like, that makes sense.
You're on board, so you're on.
Yeah, I'm good.
Okay, now, thinking about it, so we do understand this concept that we have visits nested within patients. So your entity has one-to-many things. If something has one-to-many things, those one-to-many things are nested in that thing that it belongs to.
So I have to think, because of what Fernando told me about variables and observations, that helps a lot. So what we're talking about is, well, roll with me for 1 second. What we're talking about is like, you have observations, your patients,
Mhm.
within which or whatever, there are other observations.
Yes.
So that's how that's nested. Like,
Okay.
we're not talking about variables and things, we're
No, I'm
talking
just-
about the observations.
Yes.
And observations within observations.
Yes.
Okay, that's helpful.
Okay, good. All right. Now, here, do you believe your patient is a fixed effect, or is your patient, or are your patients a sample of all possible patients? It's the latter, right?
Yeah.
Obviously.
Yeah.
So if you believe that your patients or the people for whom you're studying don't represent all the levels of the things that you're studying, you have the option of treating it as a fixed effect or a random effect. My recommendation is treat it as a random effect. Because you're going to... Okay, go ahead.
No, why would you have the option?
Because there's
You
no
just said-
statistics police who are going to come and arrest you for making one decision versus another.
No, I understand that, but
So I guess when would you make it?
When would you make that? This is based on what you believe about your data. So if you believe your patients are random, they are a subset of the total, then you could, or I would argue ought to, think of them as a random thing.
But are patients really a random subset of the total? I mean, for,
We call this a simplifying assumption,
okay.
right?
Tim, I thought you said we never have access to the whole
Right.
population.
So in that case, it would be a,
Right, but I think, so
Okay,
when
go
you
ahead.
say male or female, like,
Yes.
those are variables.
yep,
But these are observations, and that's what's confusing me.
okay.
That I can't think of a good example of observations where I would have all of the possible levels. Like, you think of variables where, like, there's
Okay,
a finite
hold on.
number of... Okay.
Let's think of this as a clinical trial.
All right?
Where in this
Oh,
clinical
okay.
trial, you
Looking at
have,
4 people.
you're looking at mortality at 4 different time points. In your study, you're only interested in survival at month 1, survival at month 2, survival at month 3, survival at month 4. Anybody who lives after month 4, they're on borrowed time, you're not interested because these are stage 4, really sick patients, they're gonna die. Fair enough?
Yeah.
Fixed effects. Time, in this case, would be a fixed effect. Month 1, month 2, month 3, and then month 4. You with me? Okay, all right. Good?
But before you were saying that the patient itself was the random.
Yep, and I'm still saying patient is the random effect.
But if you're using the patient at the different time,
Yes.
the characteristics of that patient, is that a fix? Like you wanted to,
Yes!
sorry.
Yes! So the characteristic of patient 1, because these are all of these 4 measurements are taken on the same patient, it's likely that these outcomes are going to be correlated with each other. Why?
They die in time 1, then you know what's going to happen.
Yeah.
Well,
It's the same person.
because it's the same
Yeah.
person.
Yeah.
If it's not mortality, pretend it's, I don't know, FCV, forced breathing into the tube thing. I can't talk. Right, so right, but you would expect FEV, right? That's what it is, right? Huh?
They're both, go ahead.
Yeah, okay. So, right, so you would expect that the observations would be correlated because it's the same person over time. Now, would you expect person 2 to have the same effect at time 1, 2, time 3, time 4? Why not?
Different person.
Because maybe they started off at different spots. So maybe their starting point was random effects.
What do you mean
That's
the same effect? The same effect?
so we have the effect of drug at time 1
Yeah.
to time 2. So in our models, we could assume that effect, the difference from time 1 to time 2, is the same for patient 1 and patient 2. Let's say that it decreases or increases
Right, the percentage.
by 100 points, right? But I could start at time 1 at say 210 here and 300 here, and then go to 310, and then go to 400. The difference is still 100, but I started off at random points. Does that make sense?
Yeah, the
Okay.
baseline is the same.
Yeah.
The depth is the same.
So I think I get what you're saying conceptually about fixed and random effects, but how does that apply? Like, does that apply in how you make your model?
Yes, so let's go further with this, okay? So we have patient 1, patient 2 through patient P, right? Okay? Let's say that somewhere along the lines there's a split where you have your patients, you have your colleagues' patients. Are you going to practice medicine the exact same way as your colleague?
No.
No. So there's going to be the outcomes of your patients are then going to be, or could be, correlated to some degree because you're treating them.
Yeah. Okay.
That variability or the uniqueness that you bring to the table is going to be different from the variability than the colleague and your colleague brings to the table. So the fact that you're you and how you practice medicine and the rapport that you build with your patients and all this stuff that can lead to outcomes, your essence is going to be shared amongst your patients to some degree. And that essence of you is going to be different from your colleague's essence. Now let's say you and your colleagues work in the same hospital. Is it possible for you to do a multi-site trial? So are you and your colleague going to have some degree of correlatedness due to the fact that you work in the same hospital? You're going to follow the same protocols and you work in the same environment and the same hallway, the same ambient lighting, da 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 da. So in this case we have visits or outcomes nested within patients, patients nested within providers nested within, you can keep going up, right? And then what you can do is you can say, well, I can have fixed and random effects at each of these levels. Because let's say that you're one of these and your colleague is a one of those. Are there going to be, I would bet that there are going to be systematic differences between male physicians and female physicians. I would bet. You don't think so? I would absolutely bet the farm that that's true, right? So you ever heard that expression? I feel very strongly that that's true.
You would bet the manor.
I would wager the estate. The castle, yes, good. So what's going to happen, for example, is that I could have a random effect of you, right, because you're going to be different from your colleague, but if you're a female, there's going to be characteristics that female physicians share that are different from the way male physicians share, right? So I can have nested fixed and random effects at each of these levels.
So, but what's confusing me is what I see with male and female is I actually just see that as maybe a different level. Like
Yeah, it is a different level.
Rather than a variable within that, like your versus colleague, there's providers, and then there's like providers, like the female ones and the male ones.
Yep.
But I guess you could splice that level or slice it in different ways.
Absolutely.
So that okay.
Yeah.
So if you're looking at the doctor level, you
Yeah.
would say like, I have a fixed effect on my patient.
Yes.
And if you're looking kind of at the hospital, you could say that the doctors have a random effect on them.
Yes.
Well,
Yes.
Well, why?
It's where you're starting from, right?
Yes.
So if it's me and you're looking at my patient,
Yes.
I'm the common person, so
Yes.
it's fixed on everybody.
Right. However, we're not going to be able to estimate that per se because we're probably not going to get all of your patients.
Right.
Right? So we're measuring your random effect, or your essence is random. Because if I looked at another doctor, it would be different.
But if you were just looking at my
Just looking at you, yes.
Okay.
I could actually ignore it. I could actually ignore your essence because I haven't seen your effect on any other patients. I'm trying to cover that too.
So when you say fixed versus random, the only thing I can really understand is, am I assessing all levels or am I not assessing all levels?
That's it.
But I'm trying to figure out just like what is the
advantage?
No. What am I counting as like what level? And so I totally understand what you're saying.
Yeah.
But so I think I need more examples of like how do you like.
How do you decide?
Yeah, when you say like measure the effect, I don't know which effect you're talking, like which variable versus like, and fixed versus random. So
Okay.
could you do just a couple more examples of levels?
Let me address this.
Yeah.
So if I say measure the effect, I by definition must be talking about a fixed effect. If I'm looking at a random effect, I'm simply looking at how much variability there is in that random effect. That's all I'm saying. I can't say what is my, if I were to treat me, the treating physician, as a random effect, I can't tease out my effect. If I treat it as a fixed effect, then I could. So, with respect
The
to...
same effect, that's what I don't understand.
It's not, because you're treating them differently.
Same as what?
Like, I mean, if you're deciding, right, then
Yeah.
like you're saying that like there's something you could possibly measure, but you're deciding that it's random.
Yes.
But I don't understand how you can measure the variability of something that's random and not be able to measure the effect.
Because it's random, the mathematics get insane, so let's not go there. All right? Well, they do get insane because I actually I can write down the formula, but there's no closed form solution. I have to use maximum likelihood. I have to guess at what the real answer would be. So what I would look at is, what is the variability between these two, between all levels of these random effects? So I'm just looking at the variability. It becomes
between. So it's not like you're like looking at the variability in a vacuum of like.
Correct.
Okay.
Yeah, yeah.
Because then I think that was what's confusing.
Yeah, yeah.
If you're just like looking at one doctor, like and trying to measure their variability in
Right.
a random way.
No, you're going to compare. How many people in here? I have 20 physicians in here. You guys are going to have variability between you. And if I were to treat you guys as a random sample of Robert Wood Johnson scholar blah, 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 blahs, then you're a random effect. How much variability does your essence account for in the outcome?
So if you had like one feature of the individual physicians that you were interested in, like years in practice.
Yep, I would treat that as a
That's a fixed effect. But the rest of like the essence, as you call it, of the physician is random.
Random, yeah.
Because you're not measuring it and
Right.
trying to understand its effect.
Yes.
Oh, that makes total sense.
Yeah. That's good.
Because when you talk about variability between physicians, as you said, it's comprised of, like, that variability is comprised of an infinite number of variables, not all of which we can account for. So that's the ones that we are accounting. If we can tease out sex, then that, if we're, going to try to, the ones that we're going to try to tease out that make up for interprovider, we can treat those as fixed. But the interprovider as a whole, we're treating as random.
Right.
But then isn't everything a mixed model? Because you can't always know everything.
Yeah.
That's right. Or do you just not?
So
is that not the nomenclature?
So, it's right. So let's get back to the very first model. And again, I hate, this is why I keep going back to the very basics. Because it all gets down to the basics. And people go crazy. Oh, yeah, we haven't gotten past intro.
I don't think
It all gets down to intro. So you've seen me write down this model before, right?
Yeah.
What's the random effect?
Error.
That's your unique difference relative to the mean. So in a sense, yes, everything is a mixed model. But we would treat this as the fixed effect there. When we compute our statistics, we don't actually estimate that with fixed effects models. With random effects models, we try and estimate not what the epsilon is, but how much variability there is in that epsilon. As if that makes sense. Right? You made the same thing, same decisions that people made last semester too. Some people brought in Poisson models, some people brought in logistic regression models, and that's okay. That's why we're doing this exercise. So thank you for being brave.
Can I read you the two sentences
Yeah,
from
go
the
ahead.
article that justify why they use fixed effects? Because then it might help us understand too. So basically, they're talking about why they use their difference in difference approach, and they write, first, the difference between hospitals that is steep over time cannot be mistaken for an effect of the reform, because each hospital is compared with itself before and after reform. Because of this, hospital indicators for fixed effects were used in the logistic model.
Hospital indicators for what?
For fixed effects. Can you just now put that into back into English?
So what they did,
Yeah.
by using the difference in difference model, what they did was they essentially subtracted out the essence. The thing that I don't know what else to call it. It's a random effect, so that's confusing. I'll call it essence. Now I sound like Emeril Lagasse, but right? So they're subtracting out the essence of what could have led to some of that difference from before and after the reform. So if I've subtracted out the things that are unique to me, my idiosyncratic things, then what's left over if there's a difference?
The effect of the reform.
The effect of
You're
the
right.
reform, if I've captured all relevant variables.
But how do you know that the reform didn't affect one's essence?
You're assuming that it's an assumption.
But what about this sentence, because of this, hospital indicators are fixed effects for use in the logistic model? What's a hospital indicator?
Yeah.
So, okay, so it's here, so let's build this. So what are some characteristics of you that you believe would be fixed effects? Something that you believe has an effect on the way you practice medicine that is very likely shared between other providers?
What's like sex in providers?
Sex, what
Right,
else?
hospital indicator for fixed effects is like.
So let's
like-
talk about bed
Yeah,
size.
exactly.
What were you talking about? Bed size, you talked about occupancy.
Well, it's not really.
What, right?
Right.
That occupancy ratio thing that you were talking about.
Variables within the.
Her sentence, I was saying, they're describing why they're using logistic, right? Because I think they're trying to say they're using a binary hospital indicator.
Right, so they say both logistic and fixed effects.
So,
They're making hospital indicator,
A
or they're
fixed
using
effect.
they're making a
binary.
fixed effect, and it's binary, so they're using.
So, if I were
The teaching,
to...
non-teaching, that would be a fixed effect. right?
Exactly.
Because there's only two.
Exactly.
Oh, so
Exactly.
when they say that is the hospital indicator, whether they were
Yes.
teaching or not teaching.
Yes.
How does that fit in with their use of resident-to-bed ratios of continuous variable?
So instead of this being teaching, non-teaching, they're going
Yeah.
to allow that ratio to be anywhere from 0 to whatever.
But I guess what I'm saying is they're doing both, right?
Yeah, you
They're
can
like
have
both-
fixed and random effects.
Oh,
So you could say, so we have bed size, occupancy.
Well, occupancy changes, so does that make it a,
No, you can have that be a time varying covariate.
you should still call it fixed
Yeah,
over, but it changes over time.
doesn't matter. We could call it a time varying covariate and allow that to change over time.
Okay.
Or we could call it a random effect and not look at its effect, but just allow for it to be variable and take into account its magnitude. They chose to treat it as a fixed effect and try and estimate its effect.
Yeah. Right, exactly. So like state is another one. What
State.
state is the hospital in?
Yeah.
I'm trying to think of an example of one that would be random and not fixed. Like a hospital indicator, what would be random? Because that makes sense.
A hospital effect that could be random.
Yeah, you know, like 'cause if I'm thinking about it, like if I can figure it out, then I
Budget.
can't think of one that would have
Budget.
more level.
Expenditures.
I'm sorry.
Budget, expenditures,
Budget expenditures.
budget or expenditures.
Yeah. So,
Income.
okay, so that would be random because there are a
And
fixed
you
number.
could treat any of these as fixed and or random.
But I just want to know conceptually if they, before treating, like if they are fixed or random. So I get that like there's a finite number of states, but like if your hospitals were located in fewer than 50, then I'm not accounting for all possible levels. So does that make it random?
If you chose it to be.
No.
See, here's
I don't know,
here's where I think we're struggling, is that you're looking for the writ large answer, and you're not going to get that from me, because it doesn't exist, right? This is science, where you have to make assumptions and go with your assumptions. That's why again, getting back to the basics, what is your view of the world? How do you view these things? And then depending on how you decide you view these variables, fixed, random, that's what you go with.
So I don't know if this is right or not, but I guess even if you thought something might be a random, making it a fixed effect would allow you to actually look at the effect up. So
Right.
that might be an advantage, just even if you didn't necessarily believe that. Okay.
Yeah. There's no right answers. There's degrees of rightness, right? And I think that's where a lot of people struggle with statistics and in general, it's that there's no right answers. There's what you believe, collect data, how will do the data fit with what you believe? So either the data are wrong or what you believe are wrong. What's more likely to be true, the data or what you believe?
The data is.
Coming from physicians, I'm not surprised to hear that.
So fixed, I think what I'm getting confused at is fixed versus random. Fixed has nothing to do whether it's time invariant or not.
Correct.
Okay. So then my understanding is like, say we're looking at the hospital and we're deciding are we going to treat it as fixed or random?
Mm-hmm.
And then basically we can start categorizing a hospital by different categorizations. Like
You can have hospitals have attributes.
Yeah,
so
attributes.
At each of these levels, factors, whatever we call them, levels, that's what we refer to them as. Levels have attributes.
Right.
So at my time could simply be my outcome. That's the attribute of that time variable. Right? At my patient level, I could have age, sex, race, all sorts of stuff that describe the characteristics of my patient. Then within my physician, I could have all kinds of attributes of my physician.
So as soon as I attribute it to like your gender or the size of the hospital, the teaching workers, I fix that component of that whatever hospital or patient. And then there's still the essence, which is the variability part, which we could still include the model by like creating a dummy variable for each individual hospital aside from the fixed.
If you, well actually yeah, so it's exactly what would happen is that each hospital is going to have an identifier, and then the way you set up these models is that you would then say we have things nested within patients, patients nested within physicians, physicians nested within hospitals. So to be able to do that nesting, you do have to have those dummy indicators.
Right.
You're not going to get coefficients for those indicators,
Right.
for those things that we refer to as random. But we're taking into account, basically what we're trying to do with these random effects here is that we're trying to say, well, these things are related. And this is what we were talking about before. If I have 4 observations within a person, and we believe the observations are going to be correlated within a person, how many independent pieces of observations do I have for a person? Do I have 4 independent pieces of data? No, you don't. I don't have 4 independent pieces of information if we believe these things are correlated. So if I were to look at the variance estimator, the denominator is biased. I don't have n independent pieces of observation. In this case, n would be 4, right? So I would be underestimating the variance. Does that make sense? So I'm taking into account, and by the way, with these mixed models, the degree to which things are correlated at each of these levels drives how many independent pieces of observation and how many independent pieces of information we have. Because in one study, I could replicate my study exactly to the T. And in one study, the intra-class correlation can be higher or lower from one study to the next. In that case, my n independent piece of the number of independent pieces of information I have will either go up or down depending on how correlated the information are. I have a whole. We're going to get into this more. I do have a whole lecture for fixed and random effects and all that. So we're getting ahead, and this is what tends to happen when we get into the advanced stuff. But we're not ready for that yet.
So,
Okay.
what was, if I were to have found a purely, you asked us to find a multi-variable?
Linear regression.
Linear regression. So no binary outcomes?
Right.
Okay, got it.
Sorry, I did it wrong.
Yeah, it's okay. Everybody does. It's okay.
I don't feel too bad.
That's okay. You don't feel too bad. That's good. Great. Okay. Okay. So, good. This was good discussion, right? This was good discussion. So let's look at what we have on our sheet here, okay?
Multivariate, right?
So let's go to that in the spirit of time. Okay. So what you have on your sheet, this is, I didn't do anything except print out my do file. Okay? So what we're going to do is we're going to do a regression together from beginning to end. Okay, we're going to do a regression together from beginning to end, and we're going to talk about what it is that we're doing at each step of the way. All right, provide rationale for why we're doing what we're doing. Uh-oh, now you sound like me.
This is multiple regression.
This is multiple regression. So everybody stand up. Everybody stand up. Stand up, stand up. Pretend we have our little graduation caps on. Take your tassel, move them from right to left. Good. Sit down. Now we're ready to go into multiple regression. Multivariable regression. We graduated. No more bivariate stuff, except in the end, that's what it really gets down to, right? Okay, good. So in my code here, I just have clear, and I do that for at the beginning of every single one of my do files. I clear it. I like to clear out memory. I'm going to change my current directory to my downloads directory. And so I'm trying to tie the Stata Lab into this course. I'm trying to make them dovetail very nicely here. Yes, ma'am?
So for that change directory,
Yeah.
the little tilde and the slash, does that just tell it find whatever has that at the end?
On my operating system, this would work for Linux and Apple.
Never mind then.
So in Linux, in real operating systems, this tilde means your home directory. So if you were to do cd tilde on an Apple, you would go to your home directory. All right, so I have a downloads directory hanging off my home directory. All right. So then what I'm going to do is I have a delimited file, a comma-separated value file, if that looks familiar for maybe one of your assignments. I have a comma-separated value. This is the command I'm going to use to read in this file. So I'm going to say in sheet using the file name. And then what is the delimiter of my file? It's a comma. So in my file, each of the fields, each of the variables are separated by a comma. Okay? So let me run that. Okay, so what's in my data set? In my data set, I have IQ, I have height, weight, brain size, and the age of my respondent. Okay, that's what we have here. I'm interested in predicting IQ based on these predictors. Okay, so this is my criterion. These are my predictors. That's how we refer to these things in regression. Then what I'm going to do is I'm going to add an identifier to each of the observations. The reason for that is because when we start diagnosing our regression, because that's what we're going to do, we're going to learn to diagnose our models, because maybe this model may or may not fit so well. The software tells us which observations are goofy. So I is going to correspond to the observation number when it tells me stuff. Okay? That's why I generate that identifier. Okay, then the first thing I'm going to do is I'm going to begin to look at the univariate statistics of each of those values. All right? So does anybody have any insight as to why I might be interested in looking at the univariate statistics of these values?
You're going to do regression, you need to know.
Pardon?
You need to know the mean.
You want to see how they're distributed?
I want to see how they're distributed. I want to look to see, do I have any missing values? If I have missing values, the default behavior in every piece of software that I know of is to drop the entire observation that has a missing value. Right? So we call that case-wise deletion. Case-wise deletion. Okay? So I'm interested in looking at my variables here. So here I have, and these are the statistics that I chose to look at. So it looks like my variables here all have a mean somewhere around 0. IQ has a mean of 1-ish. So it looks like maybe somebody turned those into z-scores or something. I'm not sure, but it kind of sort of looks like that. All right, I'm interested in minimum and maximum values to see if these things make sense to me. Right? This is all made up data, so that's why it's not going to make sense. But this is why I'm doing this. I'm looking to see if they make sense to me. If you had data for which you have subject matter expertise, you're going to say, oh, I can't have somebody who's 470 years old and nobody has an IQ of 30 unless they're a house plant. Right? So these things don't make sense. Right? I bring these up here, skew and kurtosis. I bring these up because many books, many authors, many people will tell you to do least squares regression or linear regression, that your outcome has to be normally distributed. Has anybody heard that?
Yeah, I might book.
Wrong. It's wrong. Wrong. Wrong, 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 wrong. Wrong, wrong. The only thing that we assume to be normally distributed is what? You guys know this already.
The variance.
Not the variance.
The error.
The error. That's what we assume to be normally distributed. Now, what's going to happen here is that the variance of my error is conditional on my predictors. It's going to be conditional on my predictors. So that being said, my outcome can be any flippity-floppity shape it wants to be. What I'm interested in is the normality of my errors. Right? And again, this gets back to bivariate regression, where, so this is a curve. I've just flipped it 45 degrees. Right? I've just flipped it 45 degrees. So you're used to looking at data this way. I've just taken this curve and I've rotated it 45 degrees, right? So what I'm assuming here is that the data, the errors are normally distributed around the regression line, right? I'm assuming that the variability of each of those things is the same, right? So that when I make predictions, the quality of my prediction here at, say, value 8 has the same quality as when I make a prediction up here when the value is 12. Does that make sense? Make sense? Okay.
Can I ask one thing? When
Yeah.
you say, if those people were right, or presume that those people were right, that you need an outcome that's normally distributed to use least squares regression, I could see how I might use that, because I might look at my outcome, and because I have my outcomes, and I can look at their plot or whatever I'm going to use to decide if they're normal or normally distributed or not, and then know whether or not to, like, what kind of regression to do. But unless I'm fundamentally misunderstanding, which is possible, you don't have your error until you do the regression. So this is what's confusing me. So this means I'm going to do the regression and then look at my error, and then if my errors are normally distributed, then I'm like, okay, that worked. That was valid. And if my errors are not normally distributed, then I shouldn't have been using that regression, and I'm going to use a different one. Okay.
That's why I use the words diagnosing your model.
Okay.
You don't know how everything works until you fit your model. Okay.
Right. That makes sense.
Okay. So all of those textbooks that said that the outcome has to be normally distributed. Nope, not at all. The error is normally distributed. That's the assumption that we're making. Yeah, go ahead.
And the kurtosis is the error?
The kurtosis, does anybody remember what kurtosis is?
No, like, it sounds like
The
scoliosis.
PD.
Yeah, no, you're right.
Like the PT, and then
Yes.
the tail.
It's the thickness of the tails.
Thickness.
How thickness of the, if I have very thick tails, if I have thick tails, it's gonna have a flatter peak. If I have very thin tails, that means all the scores are bundled up around the mean, which gives me a very peaked or leptokurtic distribution. If things are normally distributed, the distribution will be mesokurtic. Meso meaning many. Okay.
So how do you interpret those numbers? What are those numbers telling you?
Okay, so these values, so like at 1.96-ish,
Yeah.
is a mesocurtic distribution. So these have a little bit more variability than we would expect. Skew, if something is symmetric, it'll have 0 skew. Now, that's a great question because if you use different software, you would interpret these values differently. SAS, for example, uses what's called coefficient of skew, coefficient of kurtosis. So they actually change it, whereas Stata uses skew and kurtosis, the real skew and kurtosis. So what we're doing now is we're talking about strategies as to how to analyze data.
If things can be normal with different levels of thickness of tails, can they be normal with different levels of skewness?
Yes.
Okay.
Normal-ish.
Okay.
Different levels, all right? So here's another thing I'm going to do next. I'm going to be interested in looking at the bivariate correlations between my variables. So this is what we refer to as a SPLOM. S-P-L-O-M, SPLOM, a scatter plot matrix.
I like that one.
You like that? SPLOM. It's going to be one of those things you talk about at your next cocktail party. All right? SPLOM.
What does this mean? What about the?
So these are bivariate scatter plots.
Is SPLOM not coming up what?
SPLOM, scatter plot matrix, SPLOM.
Thank you.
All right, so here is the scatter plot between IQ and height. We're eventually going to try and predict IQ from these variables, these predictors. Yeah, it's all possible 2 by 2. So there's a reason why we're interested in looking at these variables, these matrices here. One of them is that we're interested in eyeballing the data for multicollinearity. Remember we started talking about multicollinearity? So right off the bat, I see a fairly strong association, say, between age and brain size. Right? I'm just eyeballing the data. I'm using this computer here to figure out, to be able to be on the lookout. When I diagnose my model, I'm going to be interested in where should I be looking. I'm trying to narrow down my field of search here. Right? Right? Also, age appears to be somewhat related to weight and maybe height. Right? Did we talk about a suppressor variable? What a suppressor variable is? Okay, so the other thing I'm going to be interested in is, do I see evidence of suppression? So that's my outcome. The top one is going to be my outcome variable. The middle one is going to be a predictor. The bottom one is going to be another predictor. Right? So here, using words, right, we see that x1 and y, they're going to be related to each other, right? But what about the relationship between x2 and y?
So x2 affects f1, which in turn affects f1?
Yes.
But
I'm not
X2
saying
is
effects.
not-
All I'm saying is associated.
x2 is not associated with y, correct?
Here's an important drawing. Because here's what we see is we have a predictor, a potential predictor, that we're considering putting in our model to predict y. But what I see is x2 is not at all associated with y, but it is associated with another predictor. So what happens in this case is this x2 variable suppresses, shrinks the variability of this predictor.
How do you know it doesn't magnify it?
How do I know it's not magnifying the variance?
Uh-huh.
Because what will happen when I partial it out, I now have x1 prime. Remember we spent all that time on partial and semi-partial correlations? So I'm partialing it out.
I think this actually relates to the fixed and variable conversation we had, right? Because I can think, because there's probably like a billion variables that influence x1 that might be independent of y if you just looked at them. Like, there are a million things that make me a different provider from Ben, but like one of those things is that I'm female and he's male. So what?
Okay, so the case.
That's how that relates to me. Like, is there?
So
why
here in
would
the case,
anyone want
but
us
we're
taking
making
out?
it with respect to the male-female kind of
Yeah.
a thing. We're assuming that it's related to the outcome.
Okay.
Here, what we're observing is that X2 is not related to the outcome. There's no overlap, right? But it is related to the other predictor. So what it's doing is that it's suppressing, this is why we refer to it as a suppressing variable, it decreases the variability of X1, which then artificially increases the observed relationship between X1 and Y.
Artificial.
It artificially increases the observed relationship between X1 and Y.
Right.
Does that make sense? So the other thing I'm looking for is, do I have potential suppression here? So I'm looking at age, and age appears to be related to all of the, somewhat related to all of the other predictors. But maybe if I were to fit a line to this, so this is the relationship between age and IQ, the thing of interest, right? These are pretty flat, just looking at the data. It's hard to look at it with this many observations. It's just a mess, right? But I'm eyeballing it for potential problems. I'm eyeballing it for potential problems.
So, sorry, did you say how you could see a suppressor variable?
Yeah, so what I'm going to do is I'm going to look at a combination of the data visually. And the next thing I'm going to do is I'm going to look at the correlation coefficients. I'm going to look at the correlation coefficients. Now remember here, this is just bivariate. So it's possible for, say, these two things to combine in such a way to suppress a third variable. Because things start going literally, in this case of 4 predictors, things literally go into hyperspace. The more variables we have, the more dimensions we need to think about the relationship of that Venn diagram, right? And it's possible in mathematics to go into n-dimensional space, right? So here we're just looking at bivariate. Okay, now you're my bellwether.
Okay, well, I was just thinking that sometimes, because I was thinking of the other example that you used, and how do you know that something's actually a suppressor variable rather than when like X1 and X2 are together, X2 is actually having the effect on Y,
Right.
but it didn't seem
We're
to
getting there.
before. Okay.
We're getting there. We're getting there. We're
Okay.
slowly, we're starting with what we know,
Okay.
and then we're going to introduce the new
So
stuff.
this is what you're assuming?
Yeah, this is
Okay,
what we
so
assume.
This is what you're assuming.
We assume no suppression,
Okay.
right? But what I'm trying to do now is I'm setting myself up for success,
Okay.
right?
Which one is the suppressor variable?
I don't know yet.
Oh, you're not doing that.
Oh, in this case, in this drawing,
Yeah.
X2 is the suppressor variable. It's suppressing the variance of X1, thereby increasing the observed relationship between X1 and Y.
And that is not bivariate,
This, no,
because it's 3.
because there's 3.
Okay.
So should you be concerned at this stage that there was such a strong correlation in the SLOM and then also here between age and size?
Yeah,
Okay.
Yeah.
Because it's 0.77, right?
Yeah.
Okay.
yeah.
So that's
So
a
what I'm
potential
doing,
problem.
it's a potential problem, so I'm going to be on the lookout for it.
Okay.
Now remember, what can happen in the face of multivariable regression is that these bivariate correlations, they can shrink, science can flip, things go crazy, right? Remember we did that?
Right.
So I'm just on the lookout for things. Did you have any?
I guess I just wanted to ask, if you feel pretty confident that a given variable is a suppressor variable, is it then more appropriate not to adjust for it in your multiple?
If you observe or you believe you have a suppressor, it's got to go. It's got to go because it's biasing your results. It's biased. It's giving you the wrong standard error or whatever it's suppressing. Right? Now, you would report that and say, look, we observe suppression, we refit the model, excluding the suppressor variable, and here are the new results. Right? Okay?
So
all
that table and the SLOM don't tell you anything about suppressor variables?
Not yet,
Okay.
but they give us a peek as to where I might look after I fit my regression. Okay? You guys aren't comfortable with this uncertainty stuff.
We're not.
Right, I'm getting that. Okay, now here's what I'm going to do. After I do that stuff, I'm just going to do it, right? Phil Nike would love us. We're just going to do it. So this is how I fit a regression in Stata. It's this reg is short for regress. IQ, the first variable after regress, is my criterion, and then everything after that are my predictors. Then what I'm going to do after that is I'm then going to repeat the regress command and then go comma beta. These betas are going to give me my beta coefficients. So they're going to give me my, let's do it and we'll explain it that way. And then we'll stop. So here is our regression table, our multiple regression table. Before we look at this, don't look at that. Let's look at the other stuff. Thanks, I'm going blind here. Okay? The first thing we're going to look at is the top stuff here. Okay? So the first thing, this is what we refer to as our ANOVA table, our analysis of variance table. And what this is asking is, does this model, or is this model better than nothing? Because our overall, our omnibus null hypothesis is all of the coefficients are 0. So says Siri. All right? That's what this is testing. So over here we have the number of observations that made it into the regression. Right? Because remember I said if it has a missing variable, it's going to do case-wise deletion. It's going to drop the case that has the missing value. You'll see this is our F statistic from our regression. So this has 4 degrees of freedom in the numerator and 2,896 degrees of freedom in the denominator. Where did that come from? 4. Why 4? Because there's 1, 2, 3, 4 parameters, which has this many observations or degrees of freedom left over. So this F statistic, this 3811, is 38 divided by 1. So it's the variance of the model divided by the variance of the residual. This is an enormous F statistic. So this is the p-value for my F statistic. So this says, the small p-value says, you know what? The model's better than nothing, right? Now then we get into things like practical significance, which we talked about a little bit before. This model explains 5% of the variance in the outcome. Right? Some people might say, that's nothing. But if the next best model only explains 1% of the variance, then that model's 500% better. So let's not get hung up on size here. In this case, size doesn't matter. This adjusted R squared, and again, I think I've said this before, I don't know why they still report this. The adjusted R squared penalizes you for the complexity of your model. So the more things that you put into your model, the lower your R squared will be relative to, the lower your adjusted R squared will be relative to your overall R squared. Nobody ever reports the adjusted R squared.
So it's not more correct because it's accounting for the potential that you might sign something just chance because you're looking at so many associations.
No. Okay, and then this is the root mean square error. This tells us essentially the standard deviation of our prediction error. Right? So we're going to have this regression line. What's the standard deviation of the error around that regression line? It's about 1. Okay? So that's how we interpret those coefficients. So because this value is significant, in some sense, it gives us permission then to go look at the table. So here, this is the coefficient. So this coefficient of 0.96 says, we expect IQ to go up by about 0.96 points for every 1 unit increase in height, holding weight, size, and age constant. Right? Does that make sense? The standard error is how much variability there is in this statistic, how wobbly that statistic is. Now, if you remember what the hypothesis is for each of these coefficients is that we assume that all of these coefficients are 0. We assume that there's 0. There's no relationship. So we have to test that. So we have our coefficient divided by our standard error, and that's going to give us our t-statistic. This t-statistic is going to be based on 2,896 degrees of freedom. This t-statistic of 8.54 is orgasmically significant. That means there's a lot of O's before you get your first non-zero number. And this gives us our confidence interval around that parameter estimate. Okay? This constant says when everything is 0, this is the expected value of IQ in this case. So for someone who has no height, who doesn't weigh anything, who has no brain and isn't born yet, we expect their IQ to be about 0. However, not statistically significant. So far, so good. So the question then becomes, if these things are on different magnitudes, if they're on different scales, how can I compare one variable with another? How can I compare the importance of one variable versus another? Okay. Well, to do that, what I can do is standardize everything. If I were to turn all of my values into z-scores, so if I turn IQ into z-scores, height into z-scores, weight, size, and age all into z-scores, and did the regression just using z-scores, I would get these beta coefficients. You'll notice how all of this stuff stayed the same relative to the top. Now I have a beta coefficient. So the interpretation of the beta coefficient is different from the regression coefficient. All right? So I interpret this beta coefficient of 0.21 as, for every 1 unit increase in height, what is the unit of height now that we've standardized it? It's a standard deviation. So for every 1 standard deviation increase in height, we expect a 0.21 standard deviation increase in IQ. Right?
Can you say the beta thing one more time?
Yeah, so these are the coefficients if or when we standardize all of the values in the system, in the equation system.
Gotcha.
So if they're all of the same magnitude, we can now compare the relative importance of these things. So here, this beta coefficient of 0.83 is about 4 times the size as height. Right? So I can actually rank order these things. Because they're standard deviations, I can take ratios of them. I can actually say that age is about 4 times as important as height in predicting IQ. Does that make sense? Because they are all of the same magnitude. I can now take ratios of them. Right? So in this, so it's twice as important as weight, and about 25 times more important than brain size.
So it's more common to report like those ratios than rather to then say what the beta coefficients
People don't
are?
do this.
Okay. I hadn't seen it, so I was.
That's because I don't know why people don't report these.
Okay.
But what I'm telling you now is, now you have a way of talking about what the drivers are of something, right? If we were to put these things in their original metric, brain size has a standard deviation of like 10 million, literally like 10 million. We measure it in voxels. Whereas age is what that's going to have a standard deviation of, say, 15. So the standard, the coefficient for brain size is going to be tiny. For every one voxel increase, how much IQ do we expect? Essentially nothing. We would need, say, 10,000 voxel increases to see something meaningful. So how do I compare these coefficients in a meaningful way? I standardize them. I put them all on the same metric, right? So then, now that I put them all on the same metric, I can then talk more about the importance of the relative importance of one predictor versus another, holding everything else in the equation constant. Okay?
So it's good practice to do that.
Huh?
It's really good practice.
Oh, I absolutely think so. Nobody does it though.
Nobody does it or he reports it?
Nobody, I don't know. They don't report it, so I assume they don't do it. I assume they don't do it. Because if you did it, why wouldn't you report it? Because it allows you to make a richer analysis of the data instead of just saying, oh, for every inch height, your IQ, we would expect to increase by about a point. Whoop-de-doo, right? Well, how about these things? How about the other things in the equation? Right? So what we're trying to get at here is we're trying to squeeze information out of the data. Right? So instead of just reporting the coefficients, which you should, and interpret them for your reader, I would recommend you also